Chapter 4. Last time we finished up to subroutine. We are going to cover lookup table, an array, and then timer and delay. Hopefully we can finish by this video lecture, part 5. Right, lookup table or create array. There is a nice feature in the instruction set that allows you to use a data table. A data table is basically a list of data values where each data is read depending on some criteria. For example, if you need to display number 5, okay, in a 7-segment display, as you can see down here, 7-segment display is characterized by the arrangements of the LED. So, okay, just assume this is that number 5 we have to send 6D to port B, right? Okay, like I said just now, it depends on the circuit configuration and truth table. How do you wire that each LED, and how do you define that A, B, C, D, E, F, G, and H? Right. Okay, this can be done using lookup table and array, besides many other methods. Okay, so what we are doing here today is to create an array. And how do we call them? Okay, for example, we have now we define a program counter EQU 0 times 02, and then number equals to 05. So we put number into W working register, and here we call the table. So the table is the indicator or an array. Okay, in this case, an array that we want to look for is number 5. Okay, number 5 is represented by 7-segment display. You have to send 6D, that it will show number 5. Okay, if you want to display number 3, you have to send 4F. Okay, then you will display number 3 on the 7th segment. So for this case, we are going to display number 5. So what is the code or the binary number for number 5 to display on the 7th segment LED? So as you see here, number 5 should be 0 times 60. But how the program search that number in this table? Okay, when you call the table, all right, so your double working register is already 05, right? Okay, your working register is having this number 05. Okay, and then when you go into the subroutine table, add WF PCF. So PC is 02. 02 is showing this. Let's say this is 0 times 30. Okay, 0 times 31. 33, 34, and so on. Okay, 31 is here, 30 is there, 32 is here, 33 is here. So this is actually the program counter. Okay, 0 times 02, this is the address or the memory location. Okay, remember we have this bank 0 and bank 1, 000102. Okay, so program counter is located here, right, at 02. So we use this address 02, which is the address, the content is the program counter. So here, when we go into this table subroutine, program counter is 30. So we want to display number 5. So 0 times 30, and then plus with 05. So it becomes 0 times 35. So what is 35? 35 is here. So from this instruction, the program counter will just jump straight to this number 35, and then return literal to W 0 times 6D. So this program will straight away go out from the subroutine, and the working register at this point is 0 times 6D. Okay, so after that you can just do another subroutine display, or just call 7 segment, whereby the number in the working register is sent to 7 segment. So what happens here is actually the number 60 just now is sent out to the 7 segment. Okay, so that's how you use that lookup table or array using RET-LW. Okay, so here is let me erase this part. So here basically it's the program called the table, and then from here add WR program counter jumps here, and then it will return from subroutine. So what happens here is that the program will not execute this part. You will just skip up to here, return from subroutine. So which means get out from the subroutine. Okay, get out from subroutine, and it will go direct to the next after the call instruction. So next instruction here, I'll just put an imaginary instruction here, call 7 segment. So this is what happens, and how easy it is to use the lookup table. Next, instruction execution time. Previously, we have covered a little bit of this in the previous chapter 2, if I'm not mistaken. We did some calculation of the clock cycle and instruction cycle of program code, particularly in delay program. Okay, so when the program is executed, it causes a delay or latency to the system. Okay, we can imagine as time requires for a system to process input until it produces desired output. Or for example, you want to turn on an LED, you need to have delay time so that you will have enough time to reveal the lights from the LED. PIC is a system based on RSC instruction set, whereby every single instruction is designed to execute within 1 cycle or maximum 2 cycles. Okay, this is what it means here is instruction cycle. Therefore, execution of the program is depend on there are 2 things: frequency of system clock, and then the length and complexity of the program. If you have more opcode or instruction, of course, the longer it is, and if you have more loop or subroutine, it will take longer. Alright, let's look at an example number 1. You have to calculate the time to execute the following lines of program. The crystal oscillator frequency is connected to PIC16F84A, and then the microcontroller is 4 MHz. Okay, assume the content of count is 5. So count. So how to do this? Count EQU 5. Right, as simple as that. And then 4 MHz, so time 1 period, okay, T equals to 1 over F equals to 1 over 4 MHz, okay, and then what is it equals to? Alright, the T cycle. T cycle here refers to the instruction cycle, right? So instruction cycle like this, for example, add LW D3, meaning you add decimal 3, okay, number 3. This is 1 clock cycle. Decrement F, skip F0, count. So count is just now it was 5, now it becomes 4 after this. 4, and then go to loop, you'll come back. Add the trill W, 3, another 3. So meaning you add, doesn't matter what the program does. What we are focusing here is on the number of loop that we are doing here, so that we can calculate how much is the clock cycle. So decrement F, skip with 0 count, and then second one will becomes 3, and then 2 and 1. After 1, when it comes 0, you will skip, go to, and go to some, and then you will do execute the next instruction after go to. Okay, here if there is an instruction here. So each line here you can have number of cycles to be calculated. For example, load at LWD3. So this, how many times it will happen? So this is one instruction cycle. Okay, times by, okay, when the count is equal to 5, 1, 2, 3, 4, 5, and then it will go out. So this will experience 5 times. Okay, so we have 5t here. And then how about this one? Okay, when count equals to 5, and count equals to 5, the first thing that comes here is after this instruction it becomes 4, right? That is first round. You go back, 3, 2, 1, 0, and then you will go out. Okay, so we have a round where 4, 3, 2, 1. Okay, so the last one, your answer is 0 already, and then you will jump, you will skip. So 0 is 2 clock cycle. From here, 4, 3, 2, 1 is 1 clock cycle, 1 instruction cycle. So we have 4 times 1 instruction cycle plus 2 instruction cycle when it's skip here. Okay, when it jumps, the result is 0, this is what happened. So that is a 2 clock cycle. So 2 times 1 equals to 6. Okay, and then loop here. How many times do we loop? Okay, for the loop will happen at 4, 3, 2, 1. So loop is a 2 clock cycle times 4. Okay, we have 1, 3, 2, 1, 2, 3, 4, and 8 instruction cycle. So this becomes 19t. So for 1 instruction cycle, we will use 1/4 megahertz times 4. Remember, 1 instruction is equivalent to 4 clock cycle. Okay, 1 instruction takes 4 clock cycle to execute. Okay, when you fetch and do all the processes. So based on this calculation, it's 1 microsecond for 1 instruction cycle. So we have 19. So 19 by 1 is, we have a total for this delay program becomes 19 microsecond. Example 2, calculate the time to execute the following lines of program. The crystal oscillator frequency connected to PIC16F84. Microcontroller is 20 MHz. Right. So first one, EQU is not an instruction. It's an assembler code whereby during assembly it will translate this into a machine or numbers. So it's not part of the microcontroller's program. So here is the first program. We have 1 cycle here, 1 cycle there, 1 cycle there. So you have 3 cycle. And then here loop. Okay, it will loop how many times? Depends on number of count. So here count is 10 and we put it into count. So it will do this like 10 times. Okay, so the first one, it will become 9, 8, 7, 6, 5, 4, 3, 0, 2, 1. And when it's 0, it will go. It will skip. So here's 9 times. So we have 1 plus 1 plus 2. Okay, we have 9 times. Plus, and the last one was 1. Okay, we have this one here, and then this one is 2. So 9 times. It will loop. The last one, loop number 10, it will go out. So plus 1 plus 2 times 1 equals 2. So what we have here, 2, 3, 4, 36 plus 3. We have 39. 39, 42. Okay, 42. So execution time is the crystal is 20 megahertz. 1 over 20 times 4, because of 4 clock cycle per instruction, times 42. Okay, so we got the final answer. Hi again. We are going to cover timer and delay for this part 5. All right. Okay, timer and delay. PIC16F84A has only one timer, and we call it timer 0. Right? It is an 8-bit timer, which when we say 8-bit, which means we have number from 00000000, which is 0, until 255. Okay. In total, we have 256 count that we can perform. Right. In order to do to use the timer, there are steps that you have to follow. But before that, why do we need a timer? Okay, a timer is useful when there is an asynchronous counter or delay is required in a program. Besides that, it is useful when you need to run something in parallel. For example, your program counter will run a code line by line. Let's say this is PC 0000, 0001, 0002, and so on. Okay, so if you use delay subroutine, let's say here is called delay, what happens is this program from here goes here and here until you call delay, and then it will go serve a delay program, and then once you finish, it will come back here. So what happens here, the program counter will stop from 003 here. It will serve this delay subroutine, and then it will come back, and then only it will continue with line number 4, which means between 3 and 4, the program was stop and do the subroutine to perform a delay. Here, which means the program is still run consecutively, but sometimes we need the delay counting to be done in parallel with the program, because there is an impact in terms of real-time program, and probably you want something that respond really fast or faster response. This is very useful. For example, if you use something like mechanical, like robots, for example, line following robots. Okay, when you change the turns, you need something to use for a delay, but you cannot do a delay in the main program. Because why? Because it will not respond to the sensor input in real time. So that's why this is the importance of timer 0 that you can use. There is one available features in the PIC microcontroller. So to set the timer, there are several steps that you need to do. First, you have to load option register setting, and then you have to load timer 0 value. This is actually initial value. Okay, and then once you have done that, you can do the interrupt register setting, INT-con. Right. Timer block diagram. This is general. If you learn about embedded system or microcontroller, this is generally are the components that is available in the timer. Okay, we have a oscillator, either external clock, and then your selection of clock. Then you have prescaler. This one is very common, and then enable timer and so on. Right. But if you would for the PIC microcontroller, this is the timer block diagram. This can be found in your PIC datasheet. Okay, you have to refer to datasheet. You will see this figure 5.1. This is basically the snapshot coming from the datasheet. So here there are two types of input, FOC4 and then RA4. RA4 is external interrupt, which come from port A 4, and this one internal clock or timer. So this one is external timer. So the timer is being controlled by TOSE, TOCS, PS21, PS0 and PSA. These are all the elements that is available in option register. Right, so item number 1, number 2, I put this as number 3 and number 4. So here, let's say if you use an internal timer, if you were to go to here, you have to select this as TOCS must be set as 0. TOSE you can set as 0 because you are not using external. So using internal, and then from here it goes to prescaler. So prescaler you have to use the table that is given for prescaler 0, 0, 0, 0 until 1, 1, 1, 1. So prescaler means you set the timer to be divided into several ratios so that you can achieve the timing that you need. So we will cover that in the next few slides later. And then we have PSA, which is to control the multiplexer here. This is the symbol of multiplexer. Multiplexer is basically selects what you want. Either this one for watchdog timer, or this one goes to prescaler is for our timer option with prescaler. And then the timer will go through synchronization, which to synchronize with the internal clocks, which requires 2 cycle of instruction cycles delay. And then the output is timer 0, either goes to data bus or it comes from the interrupt overflow bit. Right. So let's focus on this number TOSE, number 1, number 2, number 3, and number 4, because these are the points or setup in the time option register that you need to do. Okay, this is the option register, also available in the PIC datasheet. In fact, this is a snapshot from the datasheet itself. Right, so this is option register. Right, so we have bit 0 until bit 7. The first 2 is actually for other use, but not for timer. Okay, for example, this one pull up enable bit and then interrupt H select bit. Okay, we are not going to use this. So whenever you do the setup for the timer, just leave it as 0. And then TOCS. If you notice, TOCS is timer clock source select bit, which means you want to select whether this one's for external and this one's for internal. Okay, internal timer. So internal timer is basically taken from through system oscillator or system clock cycle, instruction cycle. Next is TOSE, timer 0 source edge select bit, which means you are using positive edge triggered or from low to high. So this is from high to low, this is negative edge triggered. And then the next one, 0 means like that. So if you choose 0, it will trigger when during from low to high transition. If you choose 1, it will trigger when from high to low transition. So for me, I'll just take a simple one. I'll just select as 0 from low to high, and then the previous one, the clock source bit, I'll select 0 due to I need to use the internal clock cycle. Unless if you want to use external clock source, meaning you are using from sensor or switch or external counter or whatever that you need to connect to. And then PSA, prescaler assignment bit. This one, prescaler assigned to watchdog timer 1, and a prescaler assigned to timer 0 module. If you choose 0, I will go with 0 if you were to use the prescaler assigned to the timer. Right, and then we have prescaler. So prescaler, we have 3 bit timer 0 rate, 1 to 2 ratio, 1 to 4 ratio, 1 to 8 ratio, meaning you divide like this, you divide by 2. Like this, the clock you divide by 4 and so on. Right. So later on we'll see how to calculate, to make a calculation for the timer. Okay, timer and delay, timer 0. Now let's look into how to make a calculations for the timer. Right, basically the maximum counter for the 8-bit timer is 255 decimal, meaning the numbers, the counting starts from 0 until 255. So total we have 256 counts. Right, so the timer period, if you choose the internal clock, then it will use the instruction cycle period. Remember, instruction cycle is the frequency, 1 over frequency times by 4. And then if the external clock is used, and then it based on generated period at pin RA4. Okay, if you use internal clock source, oscillator frequency of 4 MHz. So, okay, let's recall what we have calculated previously. For 4 MHz, or 1 instruction cycle is 1 over 4 MHz. You have to times by 4, remember? So, for 1 instruction cycle, it's 1 microsecond, right? So what's the maximum delay that can be generated by timer 0 is maximum count is 256 counts times the period, which is this one, okay, 1 microsecond. You will have about 0.256 millisecond. So meaning you can start timer from 0 milliseconds up to maximum of 0.256 millisecond. Right, this is assuming that you have not setting any prescaler. All right, let's try this example. If you were to generate 0.1 milliseconds delay, using timer 0 with the internal clock cycle of 4 megahertz, what will be the counter that is required? Just now the maximum is you have to count until 256. So what's the counter? The formula basically is the count or counter times the period, timer period. You will have the total time, right? So in this case, you have 4 megahertz frequency, meaning the timer period is 0.1 microsecond, and we need the total time to be 0.1 millisecond. So what is the amount of counter that we need? So the counter that we need is 0.1 millisecond, sorry. So you have 100. So the timer 0 will have to start with a certain number, okay, and then it will count until finish. If it counts from 0 until 255, then it will have a maximum of 0.256 millisecond. So right now you want to target up to 0.1 millisecond. So what is the counter that you need? Okay, so this is how the calculation is done. So you have to have 256 minus 100, and then you have a delay of 2 cycles delay. Where does that 2 cycle delay coming from? Let's go back to the previous diagram. Here you can see after all the prescaler and all that, you have a 2 cycles delay. So you have to count that, include that in your calculation. So plus 2, so it becomes, in this case, becomes 158. Right, so this is the initial value that you need to send to timer 0. How to do that? Simple, move LW. You can choose D158, easier, and then move FWF TMR0. Okay, as simple as that. Okay, so if you don't want to use decimal 158, you have to convert into hexa, which is 0 times 9e. That is up to you, up to your preference. Okay. Remember, this we have not considered the prescaler yet. Next, let's look at the prescaler. If you set your option register, okay, this is one part of the option register. Okay, whatever the value that you set here, you see the last 3 digit, okay, 0, 1, 2 is this 3-bit value, 0, 1, 2. Okay, so this is what the number that you have to set. If you were to have the timer to 1 to 2 ratio, meaning you divide by 2, or in terms of second, you the frequency divide by 2, but the time meaning you times by 2. Okay, so timer 1 incoming 1, like this one, 1 to 4, meaning incoming 1, output is 4, meaning the timer 1 microsecond you times by 4, meaning 4 microsecond, right? But in actual, you divide the frequency by 4. Like this one, you divide the frequency by 2. Okay, so you have up to maximum 1 to 256 ratio, okay, for timer 0. Watchdog timer is another thing that you might need to consider when you want to use the watchdog timer. Right, let's try to generate 0.4 milliseconds delay. Remember, just now our maximum time was 256 count times time period equals to 0.256, where the period time of one cycle is 1 microsecond. Okay, so you get 0.256 millisecond. What about if you want to have you want to generate 0.4 millisecond? So how to do that? So let's try to find the counter, the actual counts that is required. So the formula again, counter times the period, timer period, and becomes 0.4 millisecond. So the timer period is 0.1, so counter becomes 0.4 millisecond over 0.1 microsecond. So you need 400, which is exceeding the number total counts, okay, the maximum counter. So how to do it? We have to use the prescaler as I mentioned just now. So let's say we have ratio prescaler of 1 to 2 indicates it means that crystal oscillator frequency had to be divided into 2. Okay, so the timer period is 2 times instruction cycle period. Let's do some calculation to see how it goes. Let's say you have a 4 megahertz crystal and you use prescaler 1 to 2. Right, the calculation for instruction cycle is 1 over 4 megahertz, and it times by 4 for one instruction cycle, and then you divide frequency by 2, meaning you divide here, you have 2 megahertz. Okay, for 4 megahertz, megahertz, divide by 2 becomes 2 megahertz. So here, instruction cycle, it becomes 2 microseconds. Initially, when it was 4 megahertz, it was 1 microsecond. Okay, so that's how you get this. For 4 megahertz crystal, prescaler of 1 to 2, you get 2 microsecond. For 16 megahertz crystal and 1 to 4 prescaler, you get 1 microsecond. Let's calculate that. 16 megahertz, you divide by 4. Divide by 4, you get 4 megahertz. Okay, the 4 megahertz is actually equals to 1 microsecond for period. For 20 megahertz, how do you calculate that? Divide by 8. Divide by 8, what do you get? 2.5 megahertz. And then, what's the time? 1 over 2.5 megahertz times by 4. What do you get? 1.6. Okay, so that's how you calculate the timing. Okay, so 0.4 milliseconds delay can be generated using timer 0 with internal clock source of 4 MHz by prescaler 1 to 2. So for each it will be 1 microsecond. So we have the calculation. Counter times 2 microseconds, you'll get 0.4 milliseconds. So counter becomes 0.4 millisecond over 2 microsecond. What do you have? This is about 200, right? So you set the counter 200. So in order to get the 200 counter, you have to start from initial number, initial value. So 256 minus 200 plus 2. So you have about 58. So the counter will start counting from 58 until 255. Okay, when the counting starts, actually you need 2 seconds delay. So meaning here, if you minus this, you'll get about 198 or 197, and then you plus by 2, it becomes 200, meaning you will be counting for about 200 times. Right, so 58 is the number to start with in the counter timer 0. So you have to set timer 0 58. So how to do that? Move LW D58 and then move WF TMR 0. Okay, as simple as that. Or if you want to use the hexa, you have to convert 58 into hexa. It becomes 0 times 3A. Right, so basically that's about it. So the process, you load option register, okay, with the right settings, and then load the timer 0 initial value, and then after that you load INT count setting. Right, so here as usual, bank select option register, because option register is in bank 1. Move LW 0 times 08. What it means by that, you are setting this 0 times 08. 08 means 0000 1000. Here meaning you set PSA to watchdog timer. Okay, if you want to use the prescaler, okay, we're not using watchdog timer, so this should not be 1, this should be 0. So and then you need, let's say you want to have prescaler of 1 to 2, then you have to have this 0001. Let me double check, go back to the previous slides. 1 to 2 is 0000, so you have to write 000, so 0 times 00. So that's basically it with 1 to 2 prescaler. Alright, so if you don't want to use prescaler, use as this one, so 100, meaning you're not using prescaler, meaning it is 1 to 1. Okay, so if you use PSA equals to 1, so prescaler is don't care, meaning it doesn't really require it. Okay, because you set PSA. Remember, PSA, you choose 2 things, okay, the watchdog timer or prescaler. Oops. Okay, so if you choose prescaler, then you have to set the last 3 bits. If not, you just use the watchdog timer. Watchdog timer is basically for you, basically using one instruction cycle. Right, so once you have moved that into option register, next is bank cell TMR 0. Why? Because this is in bank 0. And then move LW 0 times 9E, move WF timer 0. So you put initial value to timer 0. Okay, you know this, remember this is from our previous calculation. We want to generate 0.1 milliseconds delay to the PIC microcontroller with 4 megahertz crystal frequency. So since we don't want to use prescaler, we set PSA equals to 1, so that's why we have this 0 times 08 set to the option register, and then 0 times 9E. In case if you forget, let me go back. Yeah, here. Okay. This is to create 0.1 milliseconds delay, okay, using timer with the internal clock source with crystal frequency of 4 MHz. So this is the calculation, and this is how we set it in the program code. And then move LW 0 times A0, move WFT to INT-con. So INT-con, you have to look into INT-con register. Here, let me see if I have INT-con register. Alright, here. Okay, just now we set 0 times A0. A0 is basically 10100000. So this is what it actually do. Okay, let me rewrite it here. Okay, so you set the INT-con register. So here you enable all unmasked interrupts, meaning you enable interrupt, basically global interrupt enable. So we set 1 here, and here we select disable e-wire complete interrupt. I can't recall what was this, but you have to refer to the datasheet. And then we set this one here as 1. We enable timer 0 interrupt, and then the rest as 0 0 0. Okay, and 0 0. What I'm interested in particular is this TOIF, timer 0 overflow interrupt flag bit. Basically, when you count from 0 until 255, after that it will go back to 0. Here what happens is it will trigger TOIF flag, whereby it will becomes 1. Okay, so here timer 0 will become 1 once the counter exits, meaning restarts from 255, go back to 0. Then overflow bit will be set, becomes 1. Right. So if you were to use the interrupt, this will be the indicator. Right. You have to test this bit. TOIF. How to test it? As usual, bit test F skip if set. Okay. What is this? INT-con, comma, bit number 2. Right. So, and then you can do whatever you want to do, whether you next line will be go to something, and then probably this one if set, then do the interrupt. Okay, so the rest of the program is up to you, to your needs. Right, finally towards the end of the chapter, and for now you have all the skills that you have learned before. So try to write the following simple application, okay, just to see whether or not you are able to understand what we have learned so far. So first of all, you have to write a program to write data from 0 times 0A to the RAM address of location 0 times 20 until 2F. Okay, this requires repetition, whereby you have to do some looping. And then the data to 0 times 0F from RAM's location 0 times 30 until 0 times 3F. Right, next, write another program code to calculate summation of 1 plus 2 plus C until 10. Okay, save the result in GPR, a general purpose register, at 0 times 80. Okay, and then create a program to calculate simple arithmetic problem. Save the answer at the general purpose register. 90 plus 32 times 4. Okay, so this is a simple arithmetic, but yet it's not exactly simple as you think might be. You know why? Because both of these requires multiplication, whereby your PIC microcontroller, there's no multiply instruction. So how do you go about that without multiply instruction? Let me give an example. You have a 5 times 4 is equal to 20. So how do you perform this in the assembly language? It's actually, let me write it somewhere else. I don't have enough space here. So what you do is move, first of all, move LW5, okay, and then add LW5, then add LW5, add LW5. So you add 5 4 times. So basically you get in working register, the answer will be 20. Okay, so this is a simple 5 by 4. Let's say if you have 5 by 100, so meaning you will have 100 lines. Okay, instead of doing that, you can use loop repetition. Okay, so that you will loop again and again and again. So how to do that? So you have to use counter. Counter, right? And then go to loop. So the loop is here. Sorry, the loop is here. Okay, so this is one way to do it. Not necessarily this is not necessarily the only way of doing the program code. So it's up to your creativity. That's why when I say when you write a program code, you cannot just copy the program code from somewhere else, because everyone will have their own program code, which is quite unique, because there is no one way of solving a problem into a program code. And then finally, the last exercise, imagine that you're going to record the count of 2 different switches between being pushed by a user. So you have switch A and switch B, okay, and then you have to count how many times the switch is being pressed. Okay, so you have to have the counter. Okay, so it has to be updated. Counter 2 equals to what? Okay, so number 4 is the latest one, which involves the counter or timer. Remember, you can just use the external clock for this. So this one will go to the external clock, and then it will update the timer with this using. Then you have to set whether you want to count positive edge triggered or negative edge triggered. So that is up to you. Alright, that's all for today, and let's continue with the next video later on in for chapter 5. Thank you.